Okay, so the skills that you've gotten in this chapter so far, I want to take a second and sort of do that long view. Remember how I said it's like we're climbing a mountain very slowly and you think like, yeah, okay, nothing has changed, and then you turn around and you go, holy crap, I'm really high up. So let's just look at what you've gotten under your belt in this chapter so far. So you've gotten naming and formula writing under your belt for ionic compounds, including those with multiple metallic cations, for polyatomic ionic compounds, things that have polyatomic ions, and for molecular compounds. So 3 different systems of naming, and at this point, you're pretty familiar with them. Most of you just have it now, and you can just do that as a first step to anything else. That's the first thing that you've gotten under your belt. You may not feel like you've got oxidation numbers down, but you've done them. You've had some practice with them. You've got the rules for them, and I think most of you, you've got the rules for oxidation numbers. You can probably pretty much follow the rules and assign oxidation numbers to stuff. You've gotten some practice with homework. So that's another whole skill that you've gotten in this chapter. If I give you a compound, you can find its formula mass. So it's one more thing that you've gotten under your belt here. And you took a quiz on that, and you can do that pretty easily and pretty well. And you can find the percent composition for any of the elements in a compound. Okay. We've done a lot of stuff in this chapter. There are a lot of skills that don't seem like they necessarily go together. What's amazing is how they do go together, and if I give you guys a name and ask you to find the formula mass, then you're actually practicing formula writing and finding formula mass. If I give you a name and I ask you to find the percent comp, you're actually practicing formula writing and finding formula mass and finding percent comp. So these are things that do all build on one another. And that little challenge lab that you guys did on Friday builds on all of this in a different way. It builds up to our next skill. So, great. You can find the percent composition, and we talked about when that's useful. Percent composition information is used in chemical analysis of unknown compounds. So the little Mars rover with its little chem lab sitting in its belly that pulls up a sample of Mars rock, crushes it, and analyzes it, the data that it comes back with actually is this mineral is X percent carbon, X percent nitrogen, X percent hydrogen, X percent sulfur. That's the kind of information that it returns. So we learn percent comp partly as a way to get into that sort of information, but now we're going to turn it on its head to use it the way that it's more commonly used. So before we can do that, we have to understand the difference between empirical and molecular formulas. So let's talk about that momentarily. Okay, so what you've been dealing with up to now, well, actually you've dealt with both of these, you just didn't know it. So empirical formula is just, and I know, you can read, it's the smallest whole number ratio of elements in a compound. Molecular formula is the actual number of each type of atom in a molecule. So if we talk about H2O, that's a water molecule. What is its molecular formula? The actual number of hydrogen and oxygen atoms in a water molecule. Did I just give it away? Did I just say what's the molecular formula for H2O? H2O. Yeah, this is kind of a Grant's tomb sort of question. Like, what's the molecular formula for H2O? H2O. Okay. Yeah, because there are actually 2 hydrogen atoms and 1 oxygen atom in a molecule. What's the simplest whole number ratio of hydrogen to oxygen atoms in H2O? Can you simplify the ratios there? No. That's it. It's the same thing. You can have compounds that have the same empirical and molecular formula, like water. You can also have compounds that have the same empirical formula but have different molecular formulas. So there are a whole set of things made up of nothing but carbon and hydrogen. Actually, let me do a better one. So, you know, the example I give is C2H4 and C3H6. What's the empirical formula for C2H4? If you simplify the ratios, it's CH2. So the empirical formula for that is CH2. Well, what's the empirical formula for C3H6? CH2. And similarly, we could have C4H8, we could have C10H20. Those all have the same empirical formula. Those molecules are vastly different. So C2H4 looks like that. Let me see if I can shrink this. Where C3H6 one of these would have to be single bonded. C3H6. 1, 2, 3, 4. 5, 6. That's one potential structure. You know, pretty darn different. One's got just a double bond. One has a double bond and a single bond. You get pretty dramatically different arrangements. Very different molecules. They would behave differently. They would probably have different, well, they would have different melting and boiling points. They would have perhaps different flash points, different points at which they would combust. But they have the same empirical formula. So, who recognizes this molecule? What is it? Glucose. Simple sugar made by plants using only sunlight and their wits. No, actually using sunlight and a whole series of complex chemical processes. But, okay, it's glucose, C6H12O6. What is that's the molecular formula. I cannot spell. What's the empirical formula for glucose? CH2O. So basically it's carbon and water. And if I had sulfuric acid, we could do this. Okay, not the best picture ever, but you can kind of see that there are things hiding inside other chemicals. And when we look at the empirical formula, we see that sugar is just carbon plus water. So that's great. Glucose, sucrose, fructose, those all have molecules. They all have a molecular formula. Let me ask you this. What is the molecular formula for sodium chloride? Are there molecules of sodium chloride? So what's the molecular formula of sodium chloride? There isn't one. There are no molecules. It's an ionic compound. It's a trick question. Again, ask yourself, how evil is Moser? What's the simplest whole number ratio formula for sodium chloride? NaCl. All ionic compound formulas are already empirical formulas. You've been doing empirical formulas for ionic compounds. You simplify down to the simplest whole number ratio. When we're talking about ionic compounds, there are no molecular formulas. Okay, so ionic compounds have no molecular formulas. Okay, the reason we need to distinguish between these two things is in terms of how we use that percent comp data. So we said the Mars rover takes a piece of rock into its little belly lab, crushes it up, and comes back and says this rock is 23% carbon, 14% nitrogen, 62% oxygen, and 3% hydrogen. I'm making up numbers. I doubt they add to 100. How do we use that information to find the formula of the compound? We can use it to find the empirical formula. Okay? So we can use the percent comp information to find the empirical formula. We cannot use it to find molecular formula. And we will get into how we find molecular formula. That's a whole different set of calculations. But what we're going to start off with is how we find empirical formula. And what this is going to allow you to do is to take your percent comp data from your challenge lab results, where you found out what percentage by composition, by mass, was water, and find the, whether that was .4H2O or .5H2O or .3H2O, how many units of water were in every unit of your calcium chloride. So this is what that information is going to allow you to find, and I will have you do that with your data after I've graded your labs. That'll be another couple points. So what we're going to start off with is exactly the kind of calculations that the Mars rover does in its little belly lab. We will do them a lot more slowly and a lot more painfully because the Mars rover's got some pretty fast computing ability, faster than us. So we're going to go from percent comp data to mass composition. And what that's going to give us is an empirical formula. The basic overview is for any substance that we come back with a percent comp on, we create an imaginary 100-gram sample. And that's how most students kind of attach to that and remember it is, oh yeah, finding empirical formulas where we have the magical 100-gram sample. So let me just set it up by asking you this. If I tell you that something is made of 42% carbon, if I have a 100-gram sample, how many grams of it are made up of carbon? 42. And that's why we use a sort of magical imaginary 100-gram sample to start these. Belle's going to ring in 3 minutes. Some of you are still copying this slide, so I'll let you. So we said on these, we're going to come up with a magical 100-gram sample. So, the Mars rover pulls a mineral in, crushes it, and it comes back in the lab finding that this mineral is 63.52% iron, 36.48% sulfur by mass. And what we want is the empirical formula. Now, iron sulfide, iron whatever sulfide this is, we don't know if it's iron 2 or iron 3, would be an ionic compound anyway. So when we find the empirical formula, we're actually finding the formula. So there's no other step we can even take. So if we make a magical 100-gram sample of this, what we want to know is how many moles of iron are there present for every mole of sulfur? What's the ratio of the number of moles of each substance? So we make that 100-gram sample and we figure out how many moles are represented in a 100-gram sample. So if we need to find out how many moles of iron there are, we're starting with what? Mass. Starting with mass, going to moles. So we have a magical 100-gram sample in 100 grams of whatever this stuff is. We have 63.52 grams of iron. How do you figure out how many moles of iron that is? What units in chemical go down below to cancel? Grams of iron, yeah. This is going to be grams of Fe. What units, what chemical go up above to end up in? Moles of iron. Yep. And what number goes in front of moles unless it's a given? 1. The number in front of moles shall be 1, it shall not be 0, it shall not be 2, it shall not be 6.022 times 10 to the 23rd. Okay, where do we find the number to fill in for grams? Periodic table, molar mass. What's your raw answer for the number of moles you get? Okay, we've got a raw number. We're not going to do a darned thing with that raw number. We're just going to leave it. Okay? We're just going to leave it sitting there. Now, how many moles of sulfur do we have in this same amount of this compound? Well, we have 36.48 grams of sulfur. We want to know how many moles of sulfur that is. Oops. 32.01. So let's get a raw number for moles of sulfur. Okay, so we divided the number of moles of iron by the number of moles of iron, because that's our smallest number. We get a 1. If we divide the number of moles of sulfur by the same number, what do we get? It's going to be 1.0 something, right? Who's got a number so far? Well, that's pretty darn close to a whole number 1, isn't it? And this ratio of the number of moles that we get is actually the subscript for that element. So when we go to do the empirical formula of this compound, the empirical formula of this compound is going to be Fe some subscript S some subscript. And we have that, and we have that. So this is Fe1S1. We don't write ones, so this is just FeS. So it's iron 2 sulfide. Okay. It's not difficult, but I'll tell you where people get confused. Tell you where people screw up. People want to use this number and try to make it a subscript. Can you ever have a not whole number subscript? Nope. These are whole number ratios. Once we're out past the hundredths place, we don't worry about that. We can round that. We cannot round something like 1.5. Okay? And we're going to do an example where we come up with a ratio that's like 1.5. And we're going to talk about what to do in that case. Okay. Why is this not a perfect 1? Sig figs. That number was probably 36.4872096 whatever. So it's not perfectly rounded. So we get some little amount of error, and that's okay. You know, you'll have that. But yeah, once we're out past the hundreds, we can round. That's not a concern. But you're always going to end up with, you know, like 1.002, 3.001, or 2.99937 something. That's 3. Okay, once we're out past that hundredths place, yeah, you can round. It's fine. Okay, let's do another one. Okay, so we're given data like this. 26.56% potassium, 35.41% chromium. The balance of the compound is oxygen. So obviously the first thing we have to do is figure out what percentage is oxygen. You will see problems like this sometimes, and this is the one and only case where you can just add them up and subtract from 100. So what percentage oxygen do we get? Okay, so we get 38.03% oxygen. Okay, since we're going from percent comp to an empirical formula, what's our first step? Poof! By magic, we have what? 100 gram sample. We have a 100 gram sample as if by magic. So in that 100 gram sample, we want to know how many moles of each of these exist. So 26.56 grams of potassium is how many moles of potassium? 35.41% chromium is how many moles of chromium? and 38.03, oops, did I put in percent there? Grams. Grams of oxygen is how many moles of oxygen? So I'll let you get those numbers for yourself. If we were doing this real stepwise, we would say our first step is make your magical 100-gram sample. Your second step is to figure out in that 100-gram sample how many moles of each of these things you're dealing with. And your third step is to pick the number of moles that's the smallest. So which one of these has the fewest moles? Potassium. So that's going to essentially be your 1. We're going to gear everything else off of potassium. So now I'm going to take the number of moles of potassium and I am going to divide everything else by that number of moles. I'm going to get a ratio of moles. I'm going to get a ratio of moles of chromium for every 1 mole of potassium and a ratio of oxygen for every 1 mole of potassium. So I know that the ratio for potassium is what? 1. I just divided it by itself. Okay. What are you getting for the ratio of chromium to potassium? 1.00 what? 247. Okay. On and on. What are you getting for the ratio of oxygen?
3.49909.
Shoot, I forgot to record all of that. Okay, so we had 1, 1, and 3.5. We can't have that, so we have to multiply all of those by 2 to get our subscript. So we have K2Cr2O7. And what is Cr2O7? It's dichromate, which has what? A minus 2 charge. If we had potassium 1 plus and dichromate 2 minus, what would its formula be? Oh, gee, K2CrO2O7. They don't always work that way, but very often you can kind of check yourself to see if you're on the right track. Because a lot of these are polyatomic ions in compound with other things. So what I'm going to have you do now is practice these. There is one more practice problem on page 231, and it's just practice for your own purposes. But in your homework, number 36 and 37 are both percent comp to empirical formula problems. So those are good ones to get started with. And I'll give you the rest of the time to practice and work on homework. You will have a FIP quiz over this tomorrow. So you'll be finding empirical formula from percent composition tomorrow.